So welcome everybody for this. I think it's the overall second webinar we are performing. The agenda of today is that I want to show you the basic principles of our new measurement model, equivalent conicity, how to handle with it, what you will get out of it, and it's not aim of the webinar today to tell you how to interpret the results, so what they are meaning in detail. If this is required, we have the expertise in-house. So for certain cases out in the field, when you have some strange results, just send it over to us that we can help you to find the reasons for the complicated and strange results you get there. So let's start. The equivalent conicity model is released since, I don't know, half a year I think. We've released 6.8. It has been released. So every customer who wants to get it needs to have Calipri version 6.8 or newer. So that's one prerequisite which has to be fulfilled. So let's start with starting the Calipri application. So I open Calipri version 6.10. I have a snapshot of the pre-release, but the prerequisite is only that you have to have a CPO version 6.8 or newer. I prepared a measurement plan for that, and there we have 3 measurement points for calculating the equivalent conicity, and one of them is automatically calculating the conicity graphs. I will tell you later why this happens right away without doing any measurement, but what you get out is shown right away. You have 4 graphs. As said, I repeat it because just for the video later on that the others are also able to move. So you have 2 graphs in the upper section. This is the wheel profile of the left wheel, the rail profile of the left wheel, and with these colored lines you see the contact points during the movement of the wheel on the rail. Same for the right side, so the right wheel profile and the rail profile on the right side, and also here the contact points presented in these colored lines. On the left lower corner you get a graph which presents the difference in wheel diameter during the movement. If the wheel set laterally displaces on the rail, then also the diameters on the left and the right wheel changes relatively, and the difference between the diameters is presented here in the graph as a function of the lateral displacement. And in the right lower corner you see the equivalent conicity graph, this tangents of gamma, which shows for a certain amplitude of the wavelength the conicity value. So for the typical value of the amplitudes of 3 millimeters, you get here the value of the conicity. And this value is also the only dimension next to these graphs which are part of the measurement points for the conicity calculation. So for our point here, the EC2, which has been calculated right now, you have the equivalent conicity value of 0.16, which corresponds also to the value here at 3 millimeters. We are somewhere below 0.2, so that seems to fit. So why did you get that right away without doing any measurements? Because you have certain options for the inputs for the calculation. So I just switch. The conicity is calculated based on all the definitions in the USC 519 and the European norm 15302, because there it described how to calculate the equivalent conicity, and we have implemented it exactly according to that guideline how it should be implemented. What I already said is that you have different results. The delta R function I just said before, the difference between the radii of the two wheels. Then the equivalent conicity graph, the tangents of gamma, as well as the dimension for the equivalent conicity on a certain amplitude, normally 3 millimeters. And you need to define that you get that out several input parameters. You need to have a profile shape, a profile data of the left wheel, of the right wheel. You need the same for the rails, for the left and the right rail. You need to define profile data. You have several options. You need to have a definition of the wheel clearance, so the back-to-back distance of the wheel set. You need to have the gauge of the rails, and finally you need also to know the rolling circle diameter, not the flange diameter of the wheels, so of both of them. All of these parameters need to be defined to get some calculation of the equivalent conicity. You have now several options for this definition. You can define for all of these input parameters, so let's stay there. You can define that you want to have directly linked the measured wheel profile of the left and the right wheel with the equivalent conicity. So that can be done. Same for the rail. So right away, measured data. You have a measurement point for measuring the rail, and the profile data you measured there are used as an input parameter for the equivalent conicity. For the others, you need just to have the value. You need to have a value of the wheel clearance, and there also you can use the measured value of the back-to-back distance within your measurement plan. The gauge of the rails need to be defined as a value because we cannot measure it currently. We do not have the rail geometry model available, but there are some plans to re-implement it again, but of the rail gauge. And finally, for the rolling circle diameter, you have also the possibility to use the directly measured values of your actual wheel set during the measurement of it. So that's the first option. So you can use for almost all of the parameters measured data you are just measuring before the equivalent conicity is calculated. The second option is that you store profile data of the wheels and the rails and use the files. So you can, for example, go to your track, you measure the left and the right rail as a CSV format, so the profile data as a CSV format, and you can use those files as input value for measuring or calculating the equivalent conicity. Same for the wheel. So normally the rail profiles and the wheel profiles are measured on your tablet, and during the real measurement of the wheels, you take the files of the rail and then you get the calculation of the conicity. So for wheel profile data and rail profile data, you can use stored files out of Calipri as well. So that's the second option. And the third option is that you use for all of these parameters, or all of these input data parameters. For the wheels and the rails, you can use the models. You can use standard models of the rail. You can use EN60 or something like that for a standard rail. And also for the wheels, we have some models implemented which can be used as well. And also for the wheel clearance, the diameters and the gauge of the rails, you can also use parameters where you can later on during the measurement or during the calculation also play a bit around with those parameters and check how the conicity is behaving. So one option I missed, so therefore I'm also checking in the manual, that you have also the option that for the profile data, for the wheel profile data, as well as for the rail profile data, you just define one side only. So if you define just profile data for the left rail, and if you don't define any profile for the right rail, the left rail is used as well for the right side, but just mirrored. Same for the wheels. So if you just define only one of these two, then for the second side, the mirrored profile data is used for the other side. So a lot of options. Sounds quite complicated, but in the end it isn't. These all can be defined and must be defined in the Calipri Manager tool, which I have done already. And now let's see why we got already a result data after opening the measurement plan for the EC2, because there I did define the input in a way that everything has been defined as model data or fixed data as parameter. So the most important tab here is the input tab for the EC. So I added here a measurement point. So I will not explain how to handle with Calipri Manager, because I expect you to be used to that tool already. So I added one measurement point for the equivalent canonicity method. I named it EC2, and I just added here also that it's using from parameters or values. So as an input, as described also in the manual, you need to define the wheel profiles, the rate profiles, the wheel clearance, drag gauge, and the diameters, as said before. For that we need inputs, and I defined it that I want to refer it to the parameters. And this means that for the wheel profile L, it's linked to the parameter wheel L model. I hope you can follow. And this wheel L model is a parameter of itself. So of the EC2 measurement point, there is the parameter wheel L model, and this is used for the calculation. And there I have now the option to define for the wheel model, I want to have a wheel A, wheel B, wheel H, or wheel I. These four profiles defined in the standards I mentioned before. So in the rules how to implement the equivalent canonicity calculation, there are also these four reference models are included to prove that the results are as expected, so that our algorithm calculates the equivalent canonicity as it should be. Additionally, you have the wheel profiles which are present in our wheel shop model. Because they are already there, we also added those to the canonicity method. So for the wheel profile, I decided I want to link it to the parameters with the name wheel L model and wheel R model, and I defined it here to wheel A. So that's what's set here. For the rail profile, I did the same. I linked the rail profile R to the model of rail R, to the parameter with that name. So, and let's see for the rail section, there's also linked to the rail L and R model, and I defined it at 61. This is the one I want to have. And finally for the others four, I did exactly the same. The only difference is that it's not referring to profile data, but just to values. So I linked the wheel clearance to the wheel clearance, and the other three in the same way. And for example, the wheel clearance is here the parameter and set to 1360, so that's to the standard value, and this one is used. Let's check in the Calipri measurement application if I'm telling you the right things, because there we have a tab. I hope you also saw it already, because it's there since version 6.9 only, I assume. I can't remember in detail if it was already there in 6.8, but I don't think so. There you can check for each of the measurement points if and how measure the parameters. I got the information via the chat that it's there since 6.9 only, not in 6.8. So if you don't see that, please upgrade to 6.9 or wait for the newest release 6.10 in 6 weeks from now. Because for the equivalent canonicity calculation, it's just important to see also in the measurement application how the inputs are defined, to know what is the reference, what is used for calculating the equivalent canonicity. So you see the same here, same as in the manager. For the wheel profile L, the model is used, for the rails as well, and for the wheel clearance, drag wedge, and the diameters, it's referring to parameters. So that's what's behind. If you see the list here, and to the parameters itself, the same as in the Calipri manager, these values are used for the calculation. So if I change the profile from a wheel A to a wheel B, it's automatically recalculating, and then you get the graph again. What you get out, I said already, you get this graph. You get also the equivalent canonicity value for a certain amplitude, this YEC, this 3 millimeters value. But it can also be changed if you want to have it from a 2.2 or something like that. Then you get a different value. So let's calculate. So I get 0.692 because at 2.2 it's almost stable. You also, in the standard case, get all these plots automatically stored on the tablet PC. It's just in the path of the Calipri documents. If you open those, you have this document folder, and there is also a folder created after doing the first equivalent canonicity calculation with the name of equivalent canonicity, and below that you get all these graphs if they are defined properly. So these are stored automatically with a predefined name. I named it EC plot. Then automatically a timestamp of the measurement is added to it. I just recognized I did something wrong because I did not define the file type. It's automatically set to fig, which means that it's a figure out of the MATLAB application. So I did some definition wrong, but normally as a standard it's set to a PNG. So I just need to redefine. I want to have it called EC2.png. So this one is used as prefix, so to say, and between PNG and the EC2, automatically you get the timestamp of the measurement added. So let's check if that worked in the folder. So I had defined the EC2 plot, and as said, the timestamp is added automatically. That should be exactly the same as we've seen in the measurement application. So there, all the graphs are stored automatically, and there is one checkbox which says whether you want to see after the calculation this dialog with the graphs or not. So I can just disable this one, and as soon as I enable it again, it's opened again and recalculating the canonicity graph. So what else? For the other points, for the EC1 wheel measurement and the EC1 rail wheel measurement, I just defined the input values in a different way. I just put it there because it's differently presented in the inputs graph. So for the wheel profile L, these are, let's start differently. Let's go to the manager application first, maybe to see it there. So for the EC1, the inputs, I did the definition in a way that all the rail profile down to diameter R are still set to the models, to the parameters, but the wheel profiles are linked to the measurement points, wheel profile 1L and 1R, which are within this measurement plan. So I use real measured data, which I just going to measure in a second, for calculating the tonicity. So the rest is still set to model, to parameter values, so to more or less fixed values. So that's the only input data, wheel profile L and R, which are used from live measured values. So I said it's presented in a different way in the input section here. So the wheel profile L input is referred to the measurement point, wheel profile 1L, and these 3 dots in the end are telling us that the profile data are used there. Same for the right, but yeah, for the second measurement point. So let's do some measurements. Working. So nothing happens because for the EC1 we still miss one input. So let's measure the second wheel profile as well. So as soon as all inputs are defined, automatically the equivalent tonicity value is calculated and the graphs are presented. And as the inputs, the wheel profiles are now the measured data of wheel profile 1L and 1R. But automatically it's calculated and shown here. The same would work here for the rails. There, I don't go to the Calipri Manager application because I think it's not needed anymore. We see for the input, the wheel profile L is used exactly as before, the wheel profile 1L point cloud of this measurement, which is already measured. Go back. For the wheel profile R, I did not define any input, which means that the data of the wheel profile 1L are reused in a mirrored way of the left side. And for the rail profile, I did also the same here. I just defined a link to the rail L measurement point, which is here. And for the right side, I also used the mirrored profile data of the left side. Let's see if it works as well. So the wheel profile are already there. So the only input which is really still missing is the rail L measurement point. So now I was expecting that all inputs are defined, and luckily that's true. So the EC1 is now also calculated. The graph, let's see how it looks like. Yeah, I see here a different curve in the equivalent tonicity graph, and at 3 millimeters we are at quite high compared to that as before. But as said at the beginning, I will not tell you how to interpret the results. It's more what you get out. And if we need more information, what all these graphs mean in detail, especially if you have not ideal profile shapes of wheels and rails, just send it over to us, and we will support you in getting more understanding what's behind and why the results look as they look like. But going back to this measurement point, so we have now a value of .3 calculated. What I missed before in the input section is to mention that also the used values are shown here. So if we go for the parameter of the wheel clearance, it's shown here that it's set to 1360, or for the track gauge, and these are used from the parameter section in our case. And if I just say that I don't want to have a diameter of 900 but 899, you get a different calculation out of it. So that has a direct influence on calculating the equivalent conicity, because I defined for the inputs to use these parameters as a value, and as soon as I change values here, it's automatically recalculated and also changing the result of the conicity. So what is important here? We have here 8 input parameters which need to be defined, but additionally we have some parameters more. The amplitude for calculating the equivalent conicity is famous 3 millimeters. These are I mentioned already. From the wheel set, we have the diameters, we have the wheel clearance if they are used out of the parameter section, and additionally we have also defined the rolling circle point. We've set to a default value of 70 millimeters. It needs also to be defined. And on the track side, we have a few parameters more. We have the track gauge that we already using in the inputs, but we have also the rail count. So this 1 to 40 or 1 to 20 rail count, which needs to be defined as a decimal value. So you need to define the 1 to 40 as a 0.025 value. And normally you will not be able to enter this value because the digits of all values shown in the Calipri application are set to 2 digits only. And to be able to set it here properly, you need to define it in the settings. That in setting measurements, the precision is set to 3 digits or 4. So 2 digits are not sufficient. Yeah, you have to log in as administrator in the CPO to be able to set that. So that's just important for this rail count value because we need to define it in that way. And for 1 to 40, it leads to a value of 0.025. For 1 to 20, also the 2 digits would be sufficient. In the Calipri Manager application, you don't need to define any amount of digits because you can write as many digits you want, and these are stored as well. So if you just define the 1 to 40 value in the Calipri Manager application directly and you set this value to invisible, then it's also fine. So let's go there. We have this value here, the rail count 0.025. If it's just set to invisible, then it's stored as 0.025 and used. But it's not confusing because in case you have just 2 digits set, but defined at 0.025 value in the Calipri Manager, it's presented at 0.03. Therefore, it's a bit confusing, and I encourage you to increase the amount of digits to 3 to get not confused in that case here. So I think we are through. So that's more or less everything. The one thing is missing. If you want to use as input parameter data from files, these are also parameters. So you have to link the inputs to the file names, and there you can select which files you want to have. So, ethnicity. In the export data, some profiles. So, and that's something you should be aware of, because it's really confusing. If you select the file there, the dialog is asking you whether you want to overwrite. It's in German, I'm sorry. If you want to overwrite the existing file, that's just not true. It's not overwriting, it's really taking the file as an input, but the dialog is expecting to store data somewhere, and therefore it's asking you whether you want to overwrite it. Just say yes or no, it doesn't matter. Yes, it matters. You have to say yes, and then it's used. That's just due to the fact that this parameter for selecting a file cannot differentiate between storing or loading data, and it's always expecting that you want to store something. Also, you're just loading already stored data. So that's something you need to be aware of if you use stored data, because it's really confusing, where that it needs to be improved. So I'm at the end of the presentation. It's I think I covered everything. Okay. I just got one hint from the colleagues here in the room. If there is some profile data missing on the profile, so if I have incomplete data here, because I don't know, here you were not able to measure just some points are missing in the point cloud, you will not get any result in the equivalent canonicity. You will get an error message which tells you that the profile data are incomplete or that there are missing profile data. So then check in detail whether there are some lags in the profile, so some gaps somewhere, and remeasure the profile to get really a complete line of the profile data of the point cloud, because that's important to get an canonicity result.